Hello. Today we start the fourth unit of our course, the study of Earth's atmosphere and our water resources. Now, where did the Earth get its atmosphere? When we discussed the other terrestrial planets, we found that none of them have the kind of atmosphere that Earth has, which will sustain and nourish life. Is that right? Yes, we all owe our life to our atmosphere, which is rich in oxygen. Where did we get this atmosphere? Well, look at the beautiful atmosphere we have, the kind of scenery that it creates. Well, the present atmosphere of the Earth is probably not its original atmosphere. You see, when the stars and planets are born, the little dust and debris that is left over is about like the interstellar space, like the nebula. In other words, most of it will be dust and hydrogen and the light gases. Now, where did we get this kind of atmosphere? The original atmosphere may have been similar to the composition of the solar nebula and close to the present composition of giant planets like Jupiter and so on, which is mostly hydrogen and methane. Is that right? Probably that is what Earth had as an atmosphere to begin with. Now, this atmosphere was probably lost to space and possibly replaced by compounds that are outgassed when the Earth began to cool. Now remember, when the Earth was formed, it was a very hot, boiling liquid. And eventually it cooled down. And a liquid, which is a combination of many substances, many chemical elements, cools down. It undergoes a lot of changes and it releases a lot of gas. And probably the atmosphere started taking shape with the outgassing of the gases that are produced when the liquid surface of the Earth began to cool and solidify. Now, according to the present day understanding of our atmosphere may have come from the impacts of comets and other planetesimals rich in volatile materials. That is another possibility. Now, these are all speculations. So it is possible that the present atmosphere is the result of comets and other planetesimals hitting the Earth and evaporating their volatiles, which forms the atmosphere that we have. But still, the oxygen part of it probably was not there until plants began to grow. All right, the present composition of the atmosphere is 78% nitrogen, 21% oxygen, and about 1% other gases. Other gases include, well, I will show you a chart as we go on. The oxygen so characteristic of our atmosphere was almost all produced by plants. So in the beginning, when the atmosphere formed, there wasn't any oxygen. Oxygen that we have now is actually produced all by the plants. Compared to the radius of the Earth, the atmosphere is a very thin shell with about 99% of the mass within 32 kilometers. So most of 99% of the material of the atmosphere can be found just within 32 miles from the surface of the Earth. Well, here is a composition that we talked about. Nitrogen 78%, oxygen approximately 21%, then you have argon, neon, helium, krypton, and all of them together about 1%. Now, is that all we have in the Earth's atmosphere? Well, these are called the constant components. In other words, they don't change. Year after year and centuries after centuries, these will remain a constant. Nitrogen, oxygen, argon, neon, helium, and krypton, and so on. And there is another part in the Earth's atmosphere, that is the variable components. That's the amount vary over time and location, and some of it will vary from day to day and even within a day, like carbon dioxide, water vapor, methane, sulfur dioxide, ozone, nitrogen oxides, and so on. Particularly water vapor. The amount of water in the atmosphere keeps changing day by day. You know, when it is very humid, you know there is too much water vapor in the atmosphere. Carbon dioxide, a lot of carbon dioxide is injected into the atmosphere by human activities. And most of the sulfur dioxide, all those are variable components of the atmosphere. Although both nitrogen and oxygen are essential for human life on the planet, they have little effect on the climatic conditions. You see, the weather patterns are not determined by these elements, nitrogen and oxygen. The weather patterns are actually determined by the variable components, mainly carbon dioxide and water vapor. So, the variable components, which make up less than 1% of the atmosphere, have much greater influence on both short-term and long-term weather patterns and climatic conditions. So, in this unit, we will be actually discussing briefly all these factors. Now, variation in water vapor in the atmosphere are familiar to us as relative humidity. Now, how many of you know what relative humidity is? We will discuss that in a later chapter. Alright, water vapor, carbon dioxide, methane, nitrogen oxide, sulfur dioxide all have an important property. Now, what is that important property? They all have the property of absorbing heat emitted by the earth and re-emit it in all directions, warming the atmosphere. You see, if this is a carbon dioxide molecule, heat that is radiated from the earth will be absorbed by this. It will then radiate heat in all directions. Now, in the absence of this carbon dioxide molecule, heat radiated from the earth will simply escape to space. That means earth will be a very cold object. You see, in the absence of substances like this, water vapor and carbon dioxide in the atmosphere, which absorbs heat radiated by the earth and re-emit it in all directions, warming the atmosphere. In the absence of these, our earth would have been a very cold object. Without these gases, the surface of the earth would be about 30 degrees Celsius cooler, and I don't think any of us would have liked to live on the surface of the earth. So, carbon dioxide is an essential part of the atmosphere. It is responsible for warming the atmosphere, make it easier for us to live on the surface of the earth. But what is the problem we have now? We have too much of it. When there is too much of it, there is too much warming. Again, we will talk about that as we go on. Now, trace amounts of gases like carbon dioxide warm our planet's atmosphere enough to sustain life. Without it, life may not have been possible on the surface of the earth. Now, many people misunderstand global warming and associated with a phenomenon like this. Now, global warming is a separate process which is caused by increased amounts of greenhouse gases in the atmosphere due to the actions of people like us. We pump in a lot more of these gases into the atmosphere. All right, and that is what causes the global warming phenomenon. Now, besides gases, the atmosphere also contains other substances. What are they? It contains particulate matter like dust, smoke, volcanic ash, and tiny solid and liquid particles called aerosols. Aerosols are very tiny objects that can float in the atmosphere. They are so light that it will not fall. Now, aerosols are produced in combustion when materials burn. When there is a forest fire, for example, a lot of aerosols, tiny particles, are released, and the atmosphere gets a copious amount of aerosols that way. Now, tiny particles of salt crystals that are suspended in the atmosphere come from mist created by ocean waves. You see, when there is an ocean wave and when the waves break, you see a big spray of water, and this mist of water in the atmosphere, because they're very tiny, evaporate rapidly. And when that tiny water droplets evaporates rapidly, it leaves behind a very tiny piece of salt. So small that it is very light, it will not fall down, it will stay and float in the atmosphere. Now, these are salt particles that add to the aerosols. So this mist forms an atmospheric aerosol of seawater that evaporates, leaving solid salt crystals suspended in the air. Now, actually, these are very useful to us. These salt crystals and dust becomes well mixed with the lower atmosphere around the globe, playing an important role in the formation of clouds. Later on we will see, when I discuss that, I will ask you, do you recall what we said in today's lesson? You see, when there is lot of water vapor in the atmosphere, clouds are formed by the condensation of water vapor. Now, in order that water vapor may condense, it needs these tiny particles. They are called centers of condensation. So, salt crystals and tiny dust particles will act as centers of condensation, and they are very important for the formation of clouds. So, they actually play an important role in the climatic conditions on the surface of the earth. So, they are important for us, they are useful for us. Now, two important measurements that are atmospheric related are pressure and temperature. So, almost the rest of today's lesson we're going to spend on talking about what is atmospheric pressure and how does the temperature of the atmosphere change. Now, what is atmospheric pressure? You see, there is a big column of air standing above each one of us. And if there is some material on top of our head, that material must be exerting a force on us. Is that right? Now, if I keep a kilogram, now this is 1 kilogram. If I keep 1 kilogram mass on my head, the weight of that 1 kilogram is exerting a force on me. You see, just like that, the atmosphere is exerting a force in all directions. We are being pressed in all directions by the force exerted by the atmosphere, and that is what we call atmospheric pressure. Now, how do we define pressure? You see, pressure is defined as force per unit area. If you can consider a unit area, now what is a unit area? A unit area is an area of 1 square meter. Now, the total force acting on an area of 1 square meter is a measure of the pressure at any point around there. So, pressure is a measure of force per unit area. Now, look at this. Suppose this is the atmosphere standing on this unit area. This unit area means its length is 1 unit, the width is 1 unit. And there is a column of air standing above it, extending to about 32 kilometers. Now, the weight of all that air is a measure of the force acting on that unit area. And that force on that unit area is a measure of atmospheric pressure. Now, when we stand anywhere, this pressure is on us always, everywhere, trying to press us inward. You see, we are biologically constructed to withstand that pressure. You see, our body is made to withstand that pressure because we have internal mechanism. We have internal pressure opposing that, and we live in the equilibrium state. In other words, the external atmospheric pressure and the internal pressure balance, and we feel comfortable. Now tell me, what happens if you go to a very higher place where the atmospheric pressure is low? When you go climbing mountain, and if you are not experienced in it, you begin to bleed from your nose. I don't know if you have experienced it. Why? When the external pressure decreases, the internal pressure is more. The internal pressure will act and bring out our internal materials like blood out of you. You see that? Now, just like I told you one of the previous classes, a fish from the bottom of the sea brought to the surface will tear into pieces. Well, so all these are important matters that you must understand. So, pressure is a measure of force per unit area. Now, do you know the unit for measuring force? Force is measured in a unit called Newton. Now, let me see, how much is in Newton? You see, I showed you a 1 kilogram sitting on my hand. The force that this 1 kilogram is exerting on my hand is 10 newtons, approximately. Not exactly, but it is very accurate to say that it is very close to 10 newton. Can you believe, can you imagine that? 1 kilogram sitting on my palm is pressing me down with a force of 10 newton. All right, so you can see how much is 1 newton. So force is measured in a unit called Newton. Therefore, pressure is measured. What is the definition of pressure? Force per unit area. In other words, Newton per square meter. So the unit of pressure is Newton per square meter. Look at the way you write it. The uppercase N is for Newton per meter square. And this unit has a name. Newton per meter squared is called a Pascal, which is the name of the scientist who first studied atmospheric pressure. And we write it as uppercase P and lowercase a, Pascal. Don't forget these things. These are important information. So, what is the definition of pressure? Pressure is force per unit area. What is the unit of measuring pressure? Pressure is measured in Newton per meter squared, and it is called the Pascal. Now, what happens when you travel to high altitude where the pressure is low? I told you what happens, is that right? Now, how do we measure atmospheric pressure? We need to learn to measure atmospheric pressure. An instrument that measures air pressure is called a barometer. A barometer. So, what is a barometer? The first measurement of atmospheric pressure began with a simple experiment performed by somebody called Torricelli in 1643. Now, what is the experiment he did? Torricelli took a very long glass tube of about a meter long. You see, this is a meter. You can see it doesn't even fit on the screen. And he took a tube like this, but 1 meter long. See, this tube is very small. He took a tube of 1 meter long and filled it with mercury. So he filled it all the way to the top with mercury. And then he closed the top end and inserted that into a dish of mercury. Now, like this. You see, this is the tube he filled with mercury. Then, when it was filled with mercury, he closed the top, inverted it, and then took it into a dish of mercury and then took his finger away. Now, what do you think happened to the mercury inside the tube? Now, he noticed that some mercury fell off, but a length of mercury column stayed inside the tube. Now, the question is, what is holding that length of mercury in the tube? Tell me, what is holding that length of mercury in the tube? You see, something has to be balancing. You see, this length of mercury is exerting a pressure on the surface here. And if it is not balanced by anything else, this will fall. But obviously, this mercury is standing there, means there is some other force outside balancing that inside pressure. What is that outside force? That is the atmospheric pressure. So Torricelli made a big conclusion. What is that conclusion? He said, I want you to watch this carefully. He said, the pressure exerted by the big column of mercury, big column of atmosphere standing on top of this mercury here is exactly the same as the pressure exerted by this length of mercury column. You see, that's a very, very easy conclusion to make. So he said the pressure exerted by this length of mercury is exactly equal to the pressure exerted by the atmosphere. And so he was able to measure atmospheric pressure. Alright, so he found that the length of the column of mercury was 76 centimeter. So a length of 76 centimeter is actually supported by the atmospheric pressure. Therefore, we can say atmospheric pressure is the same as pressure exerted by a length of mercury of 76 centimeter. In other words, if I keep a length of mercury 76 centimeters on my left hand and all of the atmosphere on my right hand, the pressure exerted by both on my two hands will be the same. That is what it means. Now, Torricelli concluded that pressure exerted by the atmosphere is equivalent to the pressure exerted by that 76 centimeters of mercury. Now, I'm going to give you a couple of figures. Try and remember this. The pressure exerted by 1 centimeter of mercury is 13.3 millibars. Now, I talked to you about millibars earlier. Now, this is a unit used for atmospheric pressure. Now, how much is a millibar? Now, I'll tell you that in a minute. So, if 1 centimeter of mercury exerts a pressure of 13.3 millibars, what is the pressure exerted by 76 centimeters of mercury? In fact, the atmospheric pressure is equal to the pressure exerted by this 76 centimeters of mercury. So, the pressure exerted by 76 centimeters of mercury is 76 times 13.3, that is 1011 millibars. So, it is convenient for us to say that the atmospheric pressure is approximately 1000 millibars. 1000 millibars. I told you that some time ago. I don't know if you remember. Now, how much is a millibar? Now, look at this. 1 millibar equals 100 newtons per square meter. You see? If I have, you remember how much is this force that is on my hand? This is 1 kilogram. The force exerted by this on my hand is 10 newton. And if I keep 10 of these on a square meter, then the total force exerted by that 10 of those on that square meter will be a millibar. Now, can you imagine how much is atmospheric pressure? Atmospheric pressure is 1000 times that. So it is a tremendous amount of pressure. And we are all subjected to that tremendous amount of pressure. So 1 kilopascal equal to 10 millibars. But you must have a fair idea that if somebody asks you, you must be able to say our atmospheric pressure is about 1000 millibars. Well, I'm sure most of you have seen an instrument like this. Most homes have instruments that measures atmospheric pressure. The most common type of barometer used in homes is called the aneroid barometer. This is an aneroid barometer. Inside this instrument is a small flexible metal capsule called an aneroid cell. Now here you can see that is the aneroid cell, which has a corrugated top, and that's the kind of a small box, and it has been evacuated. So what happens is when the atmospheric pressure changes, there will be small variations in the position of this corrugated top, and that will set this point to move, and it can then be calibrated to read the atmospheric pressure. So the construction of the device, a vacuum is created inside this capsule. That a small change in the outside pressure causes the capsule to expand and contract. And as the capsule expands and contracts, it makes this pointer move on the scale, letting us know if the atmospheric pressure is increasing or decreasing. Alright, now the size of the aneroid cell is then calibrated, and any change in its volume is transmitted by springs and levers to an indicating arm that points to the corresponding atmospheric pressure. The barometer reading changes when outside weather conditions change or we go to higher altitude. Now, you know that storms are associated with low pressure. When the weatherman tells you that the barometer is falling, what does that mean? It means atmospheric pressure is decreasing. When there is a low pressure, that's an indication that we could expect a storm or rain. Well, we will talk about all that again later on. Okay, what happens to atmospheric pressure as we go higher and higher above the Earth's atmosphere? You see, pressure is caused by the weight of air standing on the surface of the Earth. That means if you keep climbing, the weight of air standing above you will become less and less. As you go higher and higher, the pressure will become less and less. Now, this is the surface of the Earth. What is the atmospheric pressure at the surface of the Earth? You can see this is 1000 millibars on the surface. Now, as you climb to a higher and higher altitude, look at that. Now here you are on top of Mount Everest, and the pressure on top of that is approximately 250 millibars. That means you climb all the way to the top of Mount Everest, the pressure has been reduced to a quarter of what is at the sea level. Alright? So atmospheric pressure on the Mount Everest is only a quarter of the pressure at sea levels. Alright, let's now talk about warming the atmosphere. We talked about it already. Is that right? Warming the atmosphere. What is responsible for warming the atmosphere? Mostly the carbon dioxide and water vapor in the atmosphere. You see, when sunlight passes through the atmosphere filters, absorbs and reflects the energy coming from the sun. In other words, the radiations that are coming from the sun. A lot of the radiations that pass through the atmosphere will pass through and reach the surface of the Earth. But a good part of it will get reflected and some part will get absorbed. Only the remaining will be transmitted so that it can fall on the surface of the Earth. Only about half of the incoming radiation reaches the Earth's surface. So remember, in the absence of the atmosphere, Earth would have been receiving a lot more radiant energy from the sun. Because of the atmosphere, only about a half of the energy that is coming from the sun actually reach the surface of the Earth. Most of the radiation that reaches the surface are absorbed. The surface absorbs the heat, absorbs the energy, and then warms up. Alright, what happens then? The warm Earth will radiate that energy back. Now, again, in the absence of the atmosphere, when the Earth radiates that energy back, all that energy will go away, will get lost. That means the Earth will be a very cold object. So rock, soil, water and ground become warmer and emit the absorbed radiation. So Earth will absorb heat radiations. Heat radiations are called infrared radiations. I have told you about that some time ago. Infrared radiations. So infrared radiations from the sun are absorbed by the Earth, and Earth then re-emits heat radiations in a slightly different wavelength. So here, the next long wave radiation, you see, the radiations that are received, absorbed, are slightly shorter wavelength. And after absorbing, the Earth will re-emit heat waves, but the wavelength will be longer. Now, what is the difference between a long wavelength and a short wavelength? A short wavelength carries more energy. A long wavelength carries only less energy. So, the energy received by the Earth, those waves are shorter than the energy radiated by the Earth. Those are longer. Now, so here, the energy from the sun is absorbed by the Earth, and the warm Earth then radiates energy. As a result, what happens is the energy that is radiated by the Earth gets absorbed by water vapor and carbon dioxide. These are the two things that absorbs, and after absorbing, what they do? They absorb these radiations and re-emit it in all directions. Look at this. This is a water molecule, which absorbs the radiations that are emitted by the Earth and then re-emit it in all directions. So that helps to warm the atmosphere. So as a result, carbon dioxide and water molecules absorb these radiations. Carbon dioxide and water molecules now re-emit the infrared radiations of their own in all directions, warming the atmosphere. The net result is that less of the energy from the sun escapes immediately. So because of the presence of these kind of gases, carbon dioxide and water vapor in the atmosphere, less of the energy received from the sun escape away from the surface of the Earth. They are being absorbed and re-emitted as infrared radiations. Alright? Now, the more carbon dioxide that is present in the atmosphere, the more energy will be bouncing back to the atmosphere. That means if you put in more carbon dioxide into the air, more heat will get trapped in the atmosphere. Is that right? We need a certain amount of carbon dioxide to keep our atmosphere warm. But if you put in more, then we will be warming our atmosphere much more than what we need. Now, the process of heating the lower part of the atmosphere by the absorption of solar radiation and re-emission of infrared radiation is called greenhouse effect. Well, in actual fact, it is slightly different from greenhouse effect. I'll tell you what greenhouse effect is. Have anybody seen what a greenhouse is? A greenhouse is a little glass house, especially used in cold countries to grow plants. What happens is the energy from the sun, the infrared radiations, can go through glass, which will be then absorbed by the soil warming up inside the glass. And the soil then radiates infrared, which are long waves and cannot go through that glass. That means that heat gets trapped and warms the air inside, making it easy for plants to grow. That is greenhouse effect. In fact, if you go into your car, in your parked car at 1 o'clock in the afternoon, will you find it comfortable to go into your car? It'll be very uncomfortable. Why? The same thing, the energy, heat energy has been entering your car through the windows and heating up the inside, the seat covers and everything else, and they then emit radiations, but those radiations are long waves, cannot escape through the windows, and that means the inside of the car will become very hot. The phenomenon of the part played by carbon dioxide and water vapor is slightly different. You see, what they do is the carbon dioxide and the water molecules will absorb heat emitted by the Earth and then re-emit it in all directions, warming the atmosphere. Well, carbon dioxide and water molecules do not trap like the greenhouse. You see, infrared radiations, they are involved in a dynamic absorption and re-emission process that increases the surface temperature. I want you to understand that very well. Well, what is the structure of the atmosphere? How does the atmosphere look as we go higher and higher? Convection currents and repeated absorption and re-emission process tend to heat the atmosphere from the ground up. Now, what is the meaning of convection current? You know that. A heated air rises and cold air comes down to receive heat. That's happening all the time in the atmosphere. So, convection currents, when the surface of the Earth gets heated, air immediately in contact with the surface will be warm and less dense. It will rise up, and cold air from the top will come down and forming the convection currents in the air. And it is this that keep the atmosphere that is warm. And how does the temperature then change? the temperature decreases with increasing altitude about 6.5 degrees per kilometer. So it is the lower part of the atmosphere that is warm because it is the surface of the earth that receives heat and re-emits it. As you keep climbing higher and higher, the temperature decreases at the rate of 6.5 degrees Celsius per kilometer. Now, this change in temperature with altitude has a name. It is called the observed lapse rate. Observed lapse rate. And that's about 6.5 degrees per kilometer. Every time you go 6.5 kilometer, every time you go 1 kilometer high, the temperature decreases by 6.5 degrees Celsius. The atmosphere of the earth may be divided into several distinct layers. The layer of the atmosphere where temperature stops decreasing with height is called the troposphere. That is the first layer of the atmosphere. Troposphere is a Greek word meaning turning layer. You see, troposphere is the region where the temperature decreases with height, and up to it only continues to a certain height, about 15-16 kilometers, and from then on the temperature begins to rise. You see, I'll tell you why it happens. So there is a turning layer. Troposphere is the layer of the atmosphere where the temperature decreases with altitude. Now here is the troposphere. This is the troposphere, which is it's about 18 kilometers, about 14 kilometers, yes. So here the temperature decreases with height until about 14 kilometers. And for about 3 or 4 kilometers, then the temperature remains almost steady. The temperature decreases with height at the observed rate until about 11 to 14 kilometers, where it begins to remain constant. So you can see this area is where the temperature begins to remain constant for some height. Now the troposphere is where all weather takes place. In fact, most of the weather conditions actually happen in the troposphere. Most of the water vapor and carbon dioxide and all these is concentrated in that part of the atmosphere. Now the air pressure at the top of the troposphere is only 10% of that at sea level. So as you climb to about 14 kilometers, the pressure is only about 10% of that at the sea level. Now above the troposphere is the stratosphere. Now that is where the temperature begins to increase. Now what makes the temperature begin to increase? Well, we must start talking about the ozone layer. You know that there is a layer above the atmosphere which contains a substance called ozone. That ozone is responsible for stopping large quantities of ultraviolet radiations that come from the sun. You see, in the absence of this ozone layer, a lot more ultraviolet radiations would have reached the earth, and more than half the population of the earth probably would have died of skin cancer. You see how various things protect and make it possible for life to continue on the surface of the earth. Now the ozone absorbs ultraviolet radiations, and the chemical reactions produced will produce warmth, will produce heat. And that's the reason why the temperature begins to increase on the troposphere. So, the temperature begins to increase on the stratosphere. Troposphere is the lower level. So, the troposphere is a region where the temperature decreases with altitude up to about 14 kilometers. Well, about 11 to 14 kilometers. and then the temperature remains steady for some height, and then in the stratosphere the temperature begins to increase. Now the thin ozone layer in the upper stratosphere has a high concentration of ozone. Actually, ozone is some kind of oxygen. You see, the normal oxygen is, we call O2. Ozone is O3. 3 atoms of oxygen joined together is what we call ozone. And that is primarily responsible for absorbing the ultraviolet radiations from the sun. So I have another diagram now here. The troposphere, the stratosphere, and this is the ozone layer. So you can see most of the weather conditions exist in the troposphere, where the temperature decreases with altitude. And you can see the white line is there, the temperature remains steady for a while, and then in the stratosphere temperature begins to increase due to the activity at the ozone layer. So in the stratosphere the temperature begins to increase with height. The temperature increase in the stratosphere is due to the interaction between ultraviolet radiations and ozone. You see, ozone is O3, that is 3 atoms of oxygen staying together. The cooler air below means, you see, the stratosphere is getting warm. That means the cooler air, as you go higher, it gets warm. That means in the stratosphere, the bottom part of the stratosphere is cooler than the top part. So the cooler air below means that consecutive layers of air are denser at the bottom. Remember, cold air is denser than warm air. So as you go in the stratosphere, go higher and higher, you are seeing the air becoming less and less denser. So the bottom layers of air in the stratosphere are denser than the top layers. Now the stratosphere contains very little moisture or dust and lacks the convective turbulence. You see, most of the turbulence exists in the troposphere, where most of the weather conditions exist. Why? Because that's where you have the water vapor, the carbon dioxide, and all that kind of materials. The stratosphere contains very little moisture and dust, and it therefore lacks the convective movement. There is no convection taking place there. That means that is a beautiful area for aeroplanes to fly, especially jet aircraft. So that is a desirable altitude for aircraft to fly because there is no turbulence there. The ozone layer absorbs the stratospheric, the ozone layer above the stratosphere absorbs the ultraviolet radiations coming from the sun. We talked about it, and without this we would have it in big trouble. Now the incidence of skin cancer increases without the protection offered by the ozone layer. The concentration of the ozone layer is not static. The amount of ozone that is present in that ozone layer is not static. In fact, I'm sure most of you know that some time ago scientists were talking about a big hole in the ozone. That means something that we do in here, especially the air conditioning materials, we call the fluorocarbons, is that right? They were interfering and destroying the ozone. And now fortunately we have been able to replace all that materials by safe materials now. And so the holes in the ozone layers are now being rebuilt. Well, ozone layer is being rebuilt. Ultraviolet radiation is absorbed by ordinary oxygen. Now, the ozone layer is not a static layer that contains a fixed amount of ozone. ozone is being constructed and destroyed in a cycle. Now this is what happens. Ultraviolet radiation absorbed by oxygen, this is the normal oxygen O2. And when the normal oxygen O2 absorbs ultraviolet, it gets broken into single oxygen atoms. And so this is the equation. A normal oxygen atom absorbs ultraviolet radiations, breaking the normal oxygen molecule into two single oxygen atoms. Now, oxygen molecules colliding, if one of these now comes and collides with this oxygen molecule, it will then become an ozone, O3. So O3 or ozone is being continuously constructed in the ozone layer. So even if we make a hole, if we stop destroying the ozone, they will be automatically built. So there is an ozone building mechanism. So O plus O2 equal to O3. You got the ozone there. So ozone combines with oxygen. Now this is again a process that goes on. The ozone O3 can combine with one oxygen atom, will produce two of these normal oxygen molecules. So this is a process that continues all the time, and the ozone layer is there to protect us. It is being constructed and deconstructed. Is that right? Now this forms a stable compound, effectively removing oxygen from the ongoing ozone forming process. Now that means Freon was the culprit in removing the ozone layer. Freon and other chemicals that make their way into stratosphere are broken down by ultraviolet radiations, releasing chlorine, which reacts with oxygen. And this forms a stable compound, effectively removing oxygen from the ongoing ozone forming process. You see, if you take this oxygen away, if you allow this chlorine to remove oxygen away from there, that means oxygen will not be then available for the ozone manufacturing process. And that is the reason why we have the ozone hole. Now, such a decreased ozone layer in the atmosphere is called a hole in the ozone layer. And concerns about the depleting ozone layer led to the Montreal Protocol. I'm sure some of you must have read about it, that resulted in the phase out of the use of Freon. Freon is no longer used in the air conditioning unit. Now, the size of the hole in the ozone layer now appears to be getting smaller. So we can be thankful about it. And this is one of the things, again, I told you, once we know what happens, we can then prepare for it. We are, as enterprising as we are, we know how to deal with disasters of this type. Again, there is a limit to our abilities to deal with these kind of disasters. Okay, now above the stratosphere, we talked about the troposphere, the stratosphere, the ozone layer. Now what comes after that? Above the stratosphere is the mesosphere. Tell me, what do you think happens to temperature as we go higher in the mesosphere? Well, there is a lot of heat generated around the ozone layer, and as you go higher, the temperature begins to decrease again. Now the molecules in this layer that have sufficient energy move off into space. Now above the mesosphere is the ionosphere, and this layer is also called the thermosphere. You see, this is the layer where atoms and molecules don't exist as ordinary atoms and molecules. They get ripped apart. They form ions, and that process generates heat. That means the ionosphere begins to warm up. So let's trace out the change in the temperatures starting from the surface of the Earth. Tell me, as you go from the surface of the Earth on the troposphere, how does the temperature change? The temperature decreases, remains a constant for a while, then it increases, again remains a constant for a while, then it decreases in the mesosphere, and thereafter increases again. Well, we will put it all together later. Now, most of the matter exists in the ionosphere in the form of electrons and ions in this layer, and that is contributing to the warmth. Now, watch how the temperature changes with altitude. I have a picture of that here. This is the troposphere. The temperature on the surface of the Earth. Now, this is the average temperature, let's say about 30 degrees Celsius. Is that right? Most part of the Earth, the temperature, the average temperature is about 30 degrees Celsius. As you go higher in the troposphere, the temperature decreases up to about, 14 kilometers. And it remains a constant for a while, about 4 or 5 kilometers. Then it increases because we are going closer to the ozone layer. It increases, remains a constant, and then in the mesosphere, the temperature decreases, and as you come to ionosphere, the temperature increases. So take a good look at this, and you must be familiar with this diagram. How does the temperature variations occur in the atmosphere as we go higher? Now, I have given you another illustration of the temperature variations by using color here. You see, the reddish color indicates higher temperature, and bluish color indicates cooler temperature. So, red almost becomes blue. The temperature decreases until about 14 kilometers, remains the same, and then increases until we reach the ozone layer, that is the troposphere, the stratosphere, and now we are at the ozone layer. And then the mesosphere, the temperature decreases. Look at the deep blue there. It decreases, reaches a low value there, and at the ionosphere, it increases. You see, over here the temperature is very high, about 300 degrees, about 300 kilometers. The temperature is about 100 degrees Celsius there. So this is the altitude, and it tells you how the temperature changes with altitude. Well, we now talked about how the temperature changes with altitude, and we will now look at the result of some of these temperature changes. The temperature changes in the troposphere is mostly responsible for most of the weather patterns that we observe. Let's now talk about winds. Wind. How is wind formed? If you look at the illustration here, you know that hot air is less denser, so air that is in contact with the land will be hot air, it will rise, and cold air from the top will come down, and you got a convection current set up in the air. The same here. Warm air, you see, during the night, water gets cooled slower than the land. Land loses heat faster than water. So during the night, land will remain cold and the water will remain warm. That means the air on the surface of water will be warm. It will rise, and the cold air will sink, will produce wind patterns. Well, wind patterns are actually produced by differentiated heating of the Earth's surface. Different parts of the Earth gets heated at different rates, and that causes hot air in hot regions to rise and cold air to sink, causing this great big motion of air masses we call winds. There are many different types of winds which we will talk about. Now, uneven heating of the Earth's surface. What is the meaning of uneven heating of the Earth's surface? The heating of the Earth's surface is not the same all over. Some places receive more heat than the others. And this is responsible for all the convection currents that are set up in the troposphere. As a local region of air becomes heated, it expands and becomes less denser. Now, a good example of convection current can be seen how a room gets heated when a heater in one part of the room heats the surrounding air. Hot air is less denser, it rises, and then cold air sinks. You can see the room gets heated uniformly due to the convection currents. Now, I have told you about how convection currents happen in water when you begin to heat it. Hot water at the bottom will be less denser, it rises, and cold air will sink. You can see convection currents setting up in water. Now what results? The differentiated heating that produces the convection currents results in three general forms of motion of air. Now, one is the upward movement in hot regions. Hot regions, air will be less denser and it will move up. 2, the sinking of air at the cooler regions. And 3, the horizontal movement between cooler and warmer regions. You see, the warmer regions, air moves up and then it moves horizontally from the warm to the cold region, and the cold then sinks. So these are the 3 major types of motions of air masses. Now, a horizontal movement of air is what we call wind. You see, the upward motion and the downward motion is not characterized as wind. So wind occurs when air moves from a low pressure region, from a high pressure region to a low pressure region. For example, during the day, the soil and the Earth's surface, the solid part of the Earth, gets very warm quickly, and the water takes a very long time to heat up. That means there is differentiated heating, uneven heating. The air at the surface of the air above the solid part of the Earth gets heated very fast. The air above water gets heated very slowly. That means a low pressure is created where the air is hot because the air rises. There's a low pressure, that means air from the water side will move towards the Earth. You see, that's the wind. Now the reverse process happens during the evening. So you have sea breeze and land breeze. That's a good example of formation of winds. The direction of wind is the direction from which it blows. A wind always blows from a high pressure region to a low pressure region, and that is the direction of wind. We will now look at the local wind patterns. There are many wind patterns that we see in many places. The upward motion of warm air creates a region of low pressure. When air gets hot and it moves up, it creates a region of low pressure, and the sinking of cold air creates a region of high pressure. And the air always moves from a region of low pressure, from a region of high pressure to a region of low pressure. The incentive is always to evenly distribute air. So if there is a region of high pressure, air would want to move to a low pressure. Now on the surface, air moves from high pressure region to low pressure region. And adjacent areas of the surface can have different temperatures because of different rates of cooling and heating. We talked about that already. Now the principal cause of these temperature differences are, what are the principal causes for the differentiated heating, for the uneven heating of the Earth's surface? One is water has almost double the specific heat of land. What does that mean? You see, if you want to heat 1 kilogram of water by just 1 degree, you need 4,200 joules of energy. Whereas, to heat land, 1 kilogram of land, you need only about a half that much heat to heat it by 1 degree Celsius. See, a lot of heat energy is needed to heat 1 kilogram of water by 1 degree. You only need about a half that amount to heat land mass by that same temperature. This is one of the major reasons for the uneven heating on the surface of the Earth. Now, water mass gets heated almost uniformly due to its transparency. You see, when heat falls on water, it can actually go through it because water is transparent. So water gets heated not only at the surface but also below the surface. Whereas a land mass, most of the heat that falls on a land mass just heats the surface. It will not penetrate into it. Now, both these contribute to, that means the land will get heated faster than the water. The third factor is water is cooled by evaporation, which keeps the body of water at a lower temperature. You know that if you keep a bucket of water outside for a long time, it becomes cold. You know how? Evaporation of water. Water at all temperatures will be turning into vapor. We will talk about that in the next lesson. And the process by which water becomes vapor is called evaporation. And evaporation actually produces cooling. You see, I have seen people who travel in train in India carry a mud pot of water, and that water will be very cold during the summer season. You know why? The mud pot has got very small pores. The water that is sort of seeping through the pores will evaporate, cooling down the entire system. Now, when you sweat and when you stand in the wind, you feel cold. Why? Because the sweat on your body evaporates. Now, evaporation needs extra heat. You see, the sweat will not evaporate if you do not supply energy to it. That means the sweat evaporating will remove heat from your body. That means you feel cold. You see, the water that evaporates takes away heat from your body. Evaporation causes cooling. So all these three factors make it possible for water to be heated very slowly and land to be heated very fast. And this is the primary reason for the differentiated heating of land mass and water mass. Now, what are land and sea breeze? I already talked about this. Now, because of the ability of the land to heat up faster than the ability of water, during the day, land will get hotter faster and the water will still be cold. That means the air above the land will be hot, it will rise, creating a low pressure on land, and the cold air, that is the high pressure region, will move towards the land. Look at that. That is the breeze coming from the sea. That's the sea breeze. And at night, the reverse process happens. You see, water has been steadily being heated, and the hot water will not lose heat as easily as land does. So at night, land will cool faster than water. That means the air above water will be warm, it will rise up, creating a low pressure on the surface of the oceans, and the air from the land will rush into that low pressure region. That is the land breeze. Sea breeze and land breeze are very common, that you all know. Changes in temperature between land and sea causes the land breeze and the sea breeze. A similar situation develops in mountain regions as the mountain slopes get warmer than the valleys, resulting in a gentle flow of air from the valley to the mountain slope during the day. You see, that's very common. During the day, the mountain slopes is warmer, so the air there will rise up, creating a low pressure, and the air from the valley will move up the mountain slope. Now, a reverse flow occurs during night. During night, exactly the reverse process happens. And during cold season, cooler, dense air collects in the valley, resulting in very cold nights. It's the same process that happens during night. And warm winds from the mountain slopes can actually disturb this accumulation, compressing it and forcing it towards lower elevations under high pressure, causing a very sharp increase in temperature. It happens within a few hours actually. Now, this wind movement is actually called Chinook, or it's called snow eater. Now, the valley was full of snow, and all of a sudden a Chinook wind from the mountainside has melted all the snow. So Chinook is the snow eater that can melt away. Now, here is the example of Chinook. The warm wind at the surface of the mountain moves down to the valleys, now eating away all the ice in there. Let's now talk about briefly on global wind patterns. You see, the global climate is actually controlled by the global wind patterns. Now, what is the global wind patterns? If you look at the equator, the regions around the equator receives maximum amount of heat, is that right? That is where the sun's energy falls mostly. And that means of all the parts of the Earth's surface, regions around the equator will be the hottest. That means air around the equator will be very warm. And what happens to warm air? Warm air will rise. And when warm air rises, it creates a low pressure region that will allow air from other regions to rush in. You see? And this is what is actually called the intertropical convergence. So, the region around the equator receives direct sunlight, the heated air rises, leaving a low pressure region at the equator, or regions around the equator. Now, moving about 30 degrees north and 30 degrees south, the warm air from the equator begins to cool and sink. Now, at the equator, the air is warm, it rises, and as it rises, it spreads to north and south, and as it goes 30 degrees south and 30 degrees north, it cools down and sinks. And the sinking air is drawn into the low pressure region created at the equator. Now, between 30 degrees latitude and the equator, most of the cooling air sink and moves back to the equator. And you can see the direction of the wind. Let me come again here. The regions around the equator gets very hot, and the air there rises, spreads to the north and south, and as they rise they cool and sink, and that sinking air is drawn towards the equator. Remember, there's a low pressure region there, towards the equator from the north and the south, and these are actually called the tropical easterlies. And the equatorial region is called the intertropical convergence zone. That is where the convergence of these wind patterns exist. Now, the air movements towards the equator are called the tropical easterlies, or they are called the trade winds. I remember very often a weatherman at NBC used to say, well, we haven't seen the rainy season yet. The trade winds are not here yet. You see, the rains are brought by the trade winds. What are the trade winds? The trade winds are the winds that comes from the north and south towards the equator. Well, look at the big global wind patterns created by the differentiated heating. I hope you understand the meaning of differentiated heating. The equator gets much more heat than other parts of the world. So regions at the equator, the air becomes very hot, it rises and spreads to the south and north, and 30 degrees south and 30 degrees north, they fall and are drawn towards the equator, causing these tropical easterlies or trade winds. Now, the trade winds coming from the south and the north meet near the equator, they converge near the equator, producing a steady upward wind. Now, this is called the intertropical convergence zone. So, this is the intertropical convergence zone, and those are the areas where you get maximum amount of rain. And most of the rainforest. Now, where are some of the rainforests? You know where these rainforests are? Well, most of the rainforest occurs around the equator. The Amazon rainforest, the Congo rainforest, they are all around the equator where the intertropical convergence zone exists. Now, at the intertropical convergence zone, rising air cools because it expands, resulting in heavy precipitation. In our next lesson, we'll talk about this. You see, when a mass of air rises, it cools down. It cools down for two reasons. One, any gas that expands produces a cooling effect. And also, when you rise, we go higher and higher, the temperature of the atmosphere falls. See, due to these two reasons, as the air rises, it cools down. And cold air that contains moisture will produce condensation and clouds. And of course, condensation and clouds produce rains. And this is the reason why torrential rains do occur in these regions. And that's the reason why we have tropical, well, big forest areas there. So tropical rainforests occur in this zone of high temperature and heavy rainfall. You can see why heavy rainfall occurs where there is high temperature. As the dry rising air reaches the upper parts of the troposphere, it begins to spread towards the north and the south. Well, between 30 and 60 degrees latitude, that is, this is 30 degrees, that is 60 degrees. So the tropical easterlies are the winds from 30 degrees to the east, well, north 30 degrees and south 30 degrees towards the equator. They are the tropical easterlies. Now, between 30 degrees and 60 degrees latitude, the winds that move towards the poles appear to curve to the east, and they are called the prevailing westerlies. So another kind of wind motion. Now, prevailing westerlies in the northern hemisphere are responsible for many of the weather movements across the United States and Canada. In fact, most of our wind patterns are created by these prevailing westerlies, because you know that you remember our latitude we talked about in the last class. We are about 28 degrees latitude. So most of the United States is to the north of the 30 degrees. So most of the weather patterns that we experience in the northern hemisphere is actually due to the prevailing westerlies. Similarly, see, we don't talk much about the south because there isn't a lot of population there. Most of the world's population is actually living in the northern hemisphere. The subtropical high pressure causes a powerful belt of wind near the top of the stratosphere called the jet stream. I'm sure most of you have heard about the movement of the jet stream. It is the jet stream that brings us the weather, is that right? We will talk about that again in tomorrow's class. Now here is a jet stream. You can see weather pattern in the United Kingdom. Now, jet streams are loops of wind that extend all the way around the earth. And jet streams develop north and south loops of waves like waves in a row. And that's what you see normally in our weather map. You see, like loops on a big wave. Waves that form on the jet stream bulge towards the pole. So the jet stream normally comes with troughs and crest. Is that right? Where air movements in one direction, you see cold air moving in one direction and warm air moving in the opposite direction. And that is the crest and trough of the jet stream. Waves that form on the jet stream bulge towards the poles and towards the equator. Now here is an example of that. This is the trough and crest of the jet stream. You can see the cold air pushing to the south and warm air pushing to the north, and that warm air, that is what produces the rain there. You see, we will talk about this in the next lesson. The warm air, when the cold air is pushing in, cold air is denser, warm air is less denser. So tell me, if a mass of cold air moves in and a mass of warm air meets it, what will happen to the warm air? The warm air will ride over the cold air. The warm air will simply be lifted up. And you know from our earlier discussions that warm air that is wet, that means that contains a lot of moisture, when you lift it up, it cools down, produces condensation and a lot of rain. So a weather front can bring in rain, and we know that in Florida. A cold front moves in means we can expect rain. Well, so this is warm, moist air. This is cold, dry air. And you can see as the jet stream moves down, as the warm, moist air produces the rain, and the cold, dry air will gradually take its place. You can see at evening you will have lots of rain. By morning it will be beautiful, pleasant and dry. Is that right? Yes, we are used to that. So warm air masses move towards the poles. ahead of a trough, and cool air masses move towards the equator behind the trough. So cool air moves towards the equator and warm air moves towards the pole, and that is controlled by the movement of the jet stream. But the development of a wave on the jet stream is responsible for the weather changes on the surface. And the major theme of our next lesson will be the weather patterns on the different parts of the earth. So, the troughs of the jet stream influence the movements of alternating warm and cool air masses over the belt of the prevailing westerlies, resulting in fair weather to stormy weather, then back again. Well, we are used to this kind of weather. Now, all these descriptions are very true for most of the United States. Well, that's about it for this lesson. We will develop more on the weather patterns and related topics in the next lesson, and I'll see you for that lesson a little later.